Alright, welcome to the video which is about the effect of the Earth's orbital motion and its rotational motion on the launch of a rocket, another dot point in the space syllabus. So some important facts to get you started. If we are viewing the Earth from above, then it is rotating on its axis in an anti-clockwise direction. And if we consider Earth's motion around the Sun in our solar system, it is also orbiting in an anti-clockwise direction. So let's consider these two pieces of information and use them to help get the best possible start in our journey away from Earth towards other planets. So let's consider this situation. This is the Sun in the middle. This is the Earth orbiting, let's ignore the other planets in between, and Mars on its orbital path. Now consider this. It takes 365 days for the Earth to complete its orbit around the Sun. It takes Mars 687 days, almost double, in its journey of orbit around the Sun. So if we want to go and live on Mars and we are launching from Earth, consider the journey takes 6 months. Let's plan our journey so that we leave Earth at a certain point around this orbit, take into consideration the half a year that it takes on the journey, and where Mars is travelling at that point in time, and then 6 months later, and organise when we should leave Earth. When we're considering the launch of a satellite, there is so much to consider. This slide is a bit of an introduction to the stages of a rocket launch, and there are certain stages that are critical and that we will cover in another section. But the launch of a satellite has so many factors taken into consideration. Two of the factors we're going to consider now is the Earth's orbital motion, anti-clockwise, and its rotational motion, also anti-clockwise. So we come now to a couple of slides later if you're clicking along, or the next slide if you're watching the video. This is such an important concept, and it's one that we will come back to, and we have already looked at: relative velocity. Let's consider this situation. We have Linda standing on a platform, and we have Elvis riding in a train. And the train is moving along the platform at 20 kilometers per hour. Now let's consider ourselves as Linda, as Linda's reference frame, or the frame of reference is Linda's. Now Elvis is not only moving within the carriage at 20 kilometers per hour, but he is also throwing a ball forwards in the same direction as the train at 30 kilometers per hour. Now, what is the relative speed of the ball being thrown to Linda? And then also consider what it is to Elvis. Have a pause, think about it, and come back for the answer. So really, the answer to this problem of relative velocity is just simple vector addition. And if we were going to have a vector for the train's velocity, it would be this red one here. And then we could add in the velocity vector of the ball, and we would add it nose to tail to that one. So it would be 50 kilometers per hour to Linda. To Elvis, the ball is only 30 kilometers per hour in a forwards direction relative to him, because he does not, in his frame of reference, consider himself to be moving. So let's consider now that if we're launching a satellite or a rocket, we want to use this benefit of vector addition to give us a kickstart on our journey. So not only do we need to consider the direction of the Earth spinning on its axis, and if we launch in the same direction, then we're adding to our velocity without using any fuel or energy. And if the planet that we're trying to get to, at the time that it takes to get there, is at a point in its orbit, then we would also use the orbital velocity of the planet around the Sun. And again, we're adding those two vectors together. And we're getting a free ride, basically, from the orbit, the rotational orbit, and the orbital motion of our planet. That's good. We want to get a free ride. We want to use less fuel and have less mass. A couple of points that you can read for yourself there. The additional velocity is pretty significant. Also, one other boost that we can get is by launching the rocket somewhere close to the equator. We're going to get the maximum additional velocity from the orbital spin at the widest point. So we try to, as much as possible, launch rockets close to the equator. However, geographically that's not always possible. All right, this slide gives a bit more mathematical detail, and what we can do when we're launching the rocket is fire rockets at certain angles to help with all of this process, and we can fire rockets in the direction to keep the satellite in the direction of the motion that we want it to be in. So there's a lot of science and a lot of maths in the launching of a rocket. Okay, the next slide gives a bit more detail and adds another graphic to this. This is what I was mentioning, the vector nose to tail addition. And also this slide is basically just reiterating that if we launch close to the equator, then we can add to that rotational boost, and there's a little video there. Okay, so that rotational motion adds a velocity boost to the rocket.